recording, and as a safety measure, you can also start the recording. Do you see a record button somewhere? Anusha, have you started the recording? I have started the recording. Just as a backup measure, you should also start the recording. All right, great. So I've muted you, Anusha, so you will not be audible. So in at any point of time, if you feel like unmuting yourself, you can unmute. And all right, just that the voice is getting recorded, so your voice will also come in the recording. And I think you should also start the recording so that in case my system crashes, there is always a backup, because probably one of the persons who is planning to attend today would like to watch the recording instead. Okay. So because I think it's working hours in US. Okay, so let's. All right. So, welcome to the session 2 of the Big Data Analytics. This Big Data Analytics course is fairly exhaustive in terms of the course content, and we will first try to go through the concepts, then we will get into the hands-on mode where we will be working together to solve various kinds of analytics problems. All right. Now, so right now we are getting acquainted with the various tools available, and then we will try to solve the problems using those tools. All right. All right. So feel free to ask questions at any point of time. Do not wait for me to stop and okay, because you can interrupt in between. All right. So yesterday, we talked about the various kinds of solutions in big data domain. There are quite a few. There's actually a myriad amount of databases, NoSQL databases. So we will try to clear the confusion amongst the NoSQL, probably tomorrow or today itself. All right? Okay. So now let's talk about the various Hadoop vendors. There are quite a few Hadoop vendors in industry, starting with Cloudera. Cloudera is the oldest one because they implemented the Hadoop 1.0. Then came Hortonworks. They implemented Hadoop 2.0. Then there's another company called Cubole. They did a couple of optimizations with Hadoop and have also implemented Hive. Then there is a third company called MapR. They also contributed couple of components to the big data in the world. Okay, so but we will just talk about the primary two. One is Cloudera. Cloudera is quite a much popular. Okay, and were the first mover in the industry and has partnered with many prominent organizations across the globe, including large organizations such as Dell. Okay, so Cloudera's enterprise data hub starts with batch processing, analytic SQL, and then basically a small search engine, machine learning, stream processing, and third party apps. Then there is a workload management, and beneath that, there are storage of any type, which is HDFS and online NoSQL. So here you see the online NoSQL, it is HBase. Here you see file system. We'll go into the detail again. I'm just giving you an overview of various vendors of of Hadoop. All right. So the other vendor of Hadoop is Hortonworks. Hortonworks is relatively new. They too provide a they too provide a data platform, and They too have many partners, including Microsoft, Red Hat, HP, NetApps, and Cloud. So we, as you can see here, they too have Pig, Hive. Basically, these are the same component. Most of these are actually the same component as what Cloudera provides. Okay, just that Cloudera provides one additional component called Hue, Hue, and Impala. And in case of Hadoop, they provide, I think, Taze, one extra component called Taze. But out of both the stacks, if I have to choose personally, I will go with Hortonworks because, okay, so I will tell you one more difference. So here, let me type it. Probably that's better to do the things. Okay, let's save it into. All right. So is the font good enough? Is this font good enough? All right. Great. So we have Cloudera on one end. Cloudera uh, provides something called Impala on top of the common things which both of them provide is starting with HDFS. We will talk about all these components as we go ahead. And so HDFS, Yarn, MapReduce, Hive, Pig, and Scoop, Flume, Oozy, and Spark, and what else did I miss anything? Hive, Pig, HBase, and Zookeeper. Okay, so these are the main stack which is common for both of them. Just that few components which are not very significant, which are provided by Cloudera. So one of them which is important is Hue, okay, and the other is Cloudera Manager, okay. And with respect to Hortonworks, all right, with respect to Hortonworks, they provide Taze plus they provide Ambari. Okay, it's open source. I'll come back to the extra things which are there. And this is not Opera open source, and this is Cloudera Manager, which is their non-open source, closed proprietary. All right. So let me explain to you. So these are the common open source products. When you buy, you go with Cloudera stack, or you go with Hortonworks. The main components which are there is same across both the stacks. Now there are few things which are specific to Cloudera and few things which are specific to Hortonworks. Okay, so out of this, the Cloudera Manager, which is for installing all these components, both I mean most of the companies actually provide an installer. So they have their provisioning tool or the installer using which you install all these common components and plus few more. In case of Cloudera, they have their manager. In case of Hortonworks, they have their manager. Kubol has their manager, and then and Mapr has their manager. So there are quite a few companies who provide this kind of things. All right. Now, so lots of companies go with Cloudera, but most of new organizations go with Hortonworks. And personally, I prefer Hortonworks because the Ambari, which is used for installation, is actually heavily simplified. It makes the life of the people who are organizing the cluster very easy. It makes the life really easy. And so that's why I prefer this stack. Okay, and so what I do generally is we install Hortonworks, and then on top of it we install Hue and other related things. Okay, so that means it completes the cycle. Impala is not too much used, neither does the days, so it doesn't matter to me. Okay, so all right, that was a quick overview of what does both of them provide. I will actually put it here. I will actually put it later. I'll do it later. All right. At the top of this notes, I will just put to do in case I have some to do left for the session so that I don't forget them. All right. Now, so both of them actually provides for searching. They provides these solar and everything. So, so that there's not much of a difference. All right. So that those were the two things that were left. Now let me just get started with the today's session. All right. Do you have any question for me at this point of time? All right. Today's session is going to be more deep dive. Are you aware of Hadoop? If you are aware of certain part and you want me to skip, you can let me know and then I can skip those sessions. Great. So let's go ahead and we will talk about. So yesterday we talked about big data in general. Then we talked about, I mean, big data when we talked about the. Were you there in yesterday's session, Anush? Yesterday? Great, great. So, okay. So in big data we talked specifically about one thing, which is distributed computing. Okay. So most of the problems which are there in industry as the data grows bigger or faster or our requirements grow complex, we cannot get the work done using one computer. Therefore, we require a distributed cluster, and that is the reason behind the whole tooling. Because because most of the systems which have been designed in past, most of the programming languages, most of the architectures, they had been designed to from the perspective of the single computer. For example, if you think about threads in Java or you think about um, multi-threaded in C++. So the assumption behind multi-threading is that the code is running on a single machine, and therefore those kind of computing paradigm are no longer applicable when you do not know whether the two parts of the code are running on the same machine or on different machine. So uh, so the conclusion is almost every component in the programming stack has been impacted the moment we tried to make everything distributed, starting with a file system till the analytics engines. Everything has been impacted. All the MATLAB kind of library, the library which help you do the analysis, they all have been badly impacted because they all had to be moved to the distributed architecture, because not every piece of code is distributable. Okay, say for example, if we want to deploy, if we have 50 computers and we are trying to compute the Fibonacci series. What is Fibonacci series? Fibonacci series is the nth term of the series is equal to the summation of previous two series to two numbers, right? So if you have a series like Fibonacci series, which you want to produce, you want to generate, and so in such case, you will have to depend upon the previous values, and the previous values are dependent on their previous values. Therefore, it is always forcibly done in a sequential manner, meaning first you will do computation of the first term, then second, then third, then fourth. So in these kind of situations, you cannot divide the work to multiple players, not even multi-threading, not even multiple machines. So there are some problems. there are some problems which are strictly not to be divided into multiple computers, but luckily, lots of problems could be divided onto multiple computers. Therefore, the whole stack of computing has been impacted by this change from one computer to multiple computer. Okay, starting with the simple problems like how to store data, then how to write to the data, how to update the data, how to read the data, how to shuffle the data, as in if you want to order something. Okay, so everything has been impacted because of these changes in the way we think. Instead of thinking in terms of one machine, we are starting to think in terms of multiple machines. All right. So, and that's where tools like Hadoop comes into play. The- Hadoop was created by dog cutting of Yahoo and who were joined by Mike Caffarella, and they built this platform based on the papers from Google and like for example Google File System, Google MapReduce, and Google Bigtable. So they created they created Hadoop based on these three papers. Actually, the dog cutting and Mike Caffarella they were trying to build a search engine. Okay, they were trying to build a search engine to similar to Google. Now, when they tried to build the search engine, they tried to crawl. They realized that it is impossible. It's impossible uh, with the current set of tools. It's impossible to build a search engine with the current file system, current current file system, current databases, current search tools. It's not possible to build a search engine which can search the whole World Wide Web. That's where they came up with. That's where they were actually stuck. At the same time, Google came up with these three papers. They published three papers. Um, Jeff Dean and Sanjay Gamawat mostly, and there are two more persons who published these three papers, and which were basically a big contribution by Google to the world. So Mike Caffarella and Dog Cutting just followed those papers and built a really great software architecture, which was called Hadoop. And the search engine they were trying to build were called Nudge, which never happened though. Okay, but Hadoop happened. So Hadoop was named after the toy elephant of dog cutting's son, and it was made open source. The biggest reason why Hadoop is popular is because it was open source. Otherwise, nobody would have known what exactly is Hadoop. Now, it's as of today, it's very powerful, it's very popular, and it is well supported. Open source does not mean that it has been thrown away. Open source means that the source code has made public so that lots of company can support it and contribute to it. And that's probably one reason that Hadoop is not going away, because it's so well supported by the community. It's so well, people have a great confidence in it, and that's the reason why people adopt. Okay, so whenever you're building infrastructure which has a lock-in behavior, you always tend to make it open source. Otherwise, nobody is going to adopt it. That's a big learning for me when I was running my own company in Hyderabad in 2008. So we also tried to make it open source, but that did not work out. So reason is any system which captures data becomes has this nature of lock-in, meaning the user is getting logged in. Therefore, user has this fear of getting logged in, and hence they wouldn't go for anything other than open source. That's why you will see that MongoDB and all other NoSQL databases, all of them are open source. If they are not open source, nobody actually knows their name as well. Now, these are frameworks to handle big data. These are for reliable, scalable, and distributed programming. What does it mean? These three keywords are probably the most important aspect. So Hadoop is a framework to handle big data. It means it is a framework under which there are many components which lie in the same framework. And all of these components which lie under this umbrella or under this framework, all of these components have these three characteristics. Only those projects get adopted by Hadoop who have these three characteristics. First, reliable, second, scalable, and third, distributed. Meaning, reliable means if one of the machine goes down, there is somebody else to take care of your computing or take care of your data. Scalable, no matter what kind of requirement you have, you can add more machines and you can get the work done. It's not that you have to replace the machine and there's a huge inertia to handle the bigger load. Also, Hadoop has been written in Java. That means it is well adopted by the people because it's not written in a language which people don't understand. And also, the other reason why Hadoop was written in Java was because it was targeted. It was targeted to become the to run on almost every kind of device. That is the reason why, as of today, there is a there is another flavor of Hadoop which is called HD Insights. HD Insights is a flavor of Hadoop which has been made to run on Windows, okay, by Hortonworks and Microsoft. So that's because the Hadoop is written in Java. All right. All right, so let's describe various components that lie under the umbrella of Hadoop. The whole game starts with Hadoop distributed file system. Okay, so I think we missed one of the screens. We will cover that screen and then we'll talk later. I think that will be better if we cover this first. All right, so let me describe all of these components one at a time and in very, very simple words in maybe a paragraph or two. So keep asking the question at any point of time. You are lucky to be the only candidate in the session, so you have luxury to ask a lot of questions. Okay, so all right. Generally, my classes are generally have around 20 candidates. Sometimes they go up to 25. All right. So coming back to the ecosystem description. So we have something called Hadoop distributed file system. It's a file system which sits on top of many computers, but the complexity of many computers is completely hidden from you. All you see is a nice, beautiful file system having a lot of folders and files. Okay, so you will always feel at home as if it's a C colon for you, like C colon or D colon or E colon in your machine. So it's a single file system, although beneath it, it's actually running. These files are located on many computers. And that, how does it work? We will explain to you in a very simple way. All right. So there is this Hadoop distributed file system on which the whole ecosystem is based on. All right. Now, on top of Hadoop distributed file system is the computing engine, meaning a framework which can run many programs in parallel, which is called yarn. Yarn runs on top of the file system because yarn stores all of the information about the program it's running in HDFS as well as whatever work it does, if it has to access the files, it accesses from Hadoop distributed file system. The coupling between Yarn and Hadoop distributed file system is very, very close. So what is Yarn? Yarn is a way to get your work done. Let's say you want to churn some data, you want to uh, query some data that you can do by using Yarn. You can execute your program on Yarn, and this program can run on multiple computers at the same time. Okay. Now, when I say you can execute your program on Yarn, you generally do not execute directly on Yarn. Instead, you use paradigms. You used the one layer above the Yarn. Okay, one of the layers is MapReduce and other layer is Spark. So you tell Spark MapReduce that here is my code, here is my logic, please execute it. Now MapReduce will take the logic in the form of map and reduces. We will talk about it quickly, and then these map and reduces are executed on the whole cluster. Okay, so MapReduce will take the map, and the way SQL database takes SQL query from you and executes it on the computer. In the similar way, MapReduce will take map and reduce from you. Map and reduce you can think of as if two programs, one is called map, another is called reduce. These two programs are taken by MapReduce from you, and then MapReduce get the work done on Yarn. Okay, so in the similar way, if you are trying to talk to Spark, then you will write the your code in Spark language. There is a way to talk to Spark. So you will write your code in terms of what Spark expects, and then Spark will get the work done using Yarn. Okay, so that's very high level. That's very high level. We'll go into a little bit more details. Okay, now, parallel to this, we have something called HBase. HBase is a database. You have file system and a database. The way on your computer you have file system like C colon, D colon, or E colon. If you are from Unix background, you have starting with the slash. There are many folders and many files, right? That is a file system. Now, there's a difference between database and file system. In case of file system, if you have to modify a particular line, you generally have to rewrite the whole file, and that becomes very clumsy. Same is the case with the HDFS. So if you just have to keep on appending to a file, then the file systems are great. But if you have to modify a particular line and update a particular line, and you have to do it quite often, then file systems are not great. That's where a database comes into play. So that's the difference between a database and file system, and same is the database difference between HBase and HDFS. HBase, the one you see on this side, it's a NoSQL database. We will cover the NoSQL database probably tomorrow. And this NoSQL database has got the property of the way the reason why we use HBase is to store hundreds of millions of records. Okay. Otherwise, if your records are, may say, a few thousand records or few hundred records or 100,000 records, even up to 10 million records, your existing databases do a very good job. But above 100 million records, your existing database or existing machines will not be able to handle that. Why? Because it's not only the problem with the database, it's also the hardware, because every machine has got hard disk, and that's where it stores data, and hard disk is slow. Therefore, reading 10 million records is almost impossible from a normal hard disk. Okay, so Hadoop distributed file system, on top of Hadoop distribution file system, we have HBase. HBase indirectly writes the data into HDFS and gets the computation done through Yarn and MapReduce. Now, HBase doesn't have a query language. Hive is the one which provides you a query language. So you write your logic in Hive that gets executed via MapReduce on Yarn. So Hive is a kind of SQL query language because lots of logic, if you are just churning data, whether the data is lying in HBase or HDFS, if you are churning the data, it's easy to write in SQL rather than for loop, while loop, or those if else conditions. So therefore you write your logic in SQL in Hive, and that logic get translated to to MapReduce by Hive and then executed over Yarn and using the file system. So similar to Hive, you have Pig Latin, which is a similar language like SQL, but very simplified language. Very simplified language. And you write your pig Latin that gets again translated into MapReduce kind of paradigm, and that gets executed on Yarn. So you write your logic in form of SQL kind of statements, and those SQL statements become kind of a MapReduce program internally, and then those MapReduce programs are executed by MapReduce on top of Yarn. Okay, so that's a quick overview about Pig and Hive. And Pig and Hive, because they are able to provide you the capability of SQL, they are also called analytics tool. Okay, so for simple tasks which can be done using SQL, the Pig Latin and Hive are good. But if the task is a little more complex, analytics task, if it becomes a little bit towards predictive analytics. What is predictive analytics? Analytics, the work where you want to do the future forecast or the prediction. Okay, in those cases, both of these do not help much. In that case, you have Mahat. In Mahat, Mahat is a collection of library functions which provide you many kind of machine learning or statistical analysis algorithms. So you could use Mahat algorithms, and there is something called Spark also. Spark provides MLlib and other libraries with which you can churn huge data and do lot of predictive analytics. We will cover all of those things as we go forward. Then we have Uzi. Uzi is nothing but a workflow engine because as we just talked, all right. So before we jump to Uzi, let's talk about two unsung heroes, which are Flume and Scoop. Flume is for moving data, moving files, moving some unstructured data from various kinds of sources to HDFS. And Scoop is for transferring data back and forth from databases to Hadoop or from Hadoop to database. What does it mean? It means that if you have data in your SQL database, you can transfer that data from SQL database to file system, or to, let's say you want to just put it in a CSV format, you can do that. As well as using Scoop, you can transfer data from from say SQL database into Hive or HBase. Now basically you can say HBase or HDFS from and to database. That's what the job of Scoop. Although it's not a rocket science, you can always write your program to read the data from these databases and put that data into the HDFS or HBase. But again, there's unnecessary work which can be easily automated using Scoop. All right. So that's about Scoop and Flume. Now comes Oozy. So when you have lot of things to do, let's say you have to do some analytics on data. Let's say you want to do predictions on data. So before you do the predictions, you will have to pull all of the data from various sources to HDFS, right? If your data is really big, so if you have to do say a predictive analytics that say, let's just take a simple case of recommendation engine. You're trying to build a nice recommendation engine. So before you start recommendation engine, all the attributes about all the behavior of users, all the detail about products, you have to gather and bring it to HDFS. So for that, you will write the Flume scripts and Scoop scripts. Also, sometimes you will end up writing HDFS shell commands, with which there are some, if you want to manually put the data via HDFS, you will do that. Okay, so once you bring in the data, you will have to clean the data either using Pig, Hive, or MapReduce, or maybe some part in Spark. So once you have cleaned the data and you have created the format which Mahat is expecting the input to be, then you will run Mahat. And then maybe once Mahat has finished the work of giving recommendation, you will like to push the recommendations, as in this person likes this thing, that person likes that thing. Those are the recommendations. So those recommendations you would like to display on your website, and to display it on your website, you have to push it to the MySQL, to your web server. So again, the results of this Mahat has to be pushed to the web server. For that, you might use the Scoop. Now you can see that in a small, in a typical analytics problem, you end up using many components parallelly. So how do you get all these components in a workflow? First do this, then do this, then do this. When this thing finishes, start this, and that kind of a workflow. If you want to build, okay, let's say you would like to build that, first finish the data parallelly using Flume and Scoop from various sources into this. And once both of the process of Flume and Scoop parallelly finish, then you start your Pig script or Hive script parallelly. Now, once that is finishes, then you say that, okay, let's start with our Mahat program. And once Mahat program finishes, then you would like to put the results of Mahat back via Scoop. So you can see that there is a workflow, there is a flow of work, flow of data in certain fashion. Number of steps have some ordering, some sequence. To do this sequence, either you write it manually, you write your own program, or you can use Uzi for that. Okay, you can use Uzi for that. And then, and also you can interact. So user can talk to Uzi, create the workflow, and get the work done over the cluster, or user can individually talk to all of these components either via command line, via Python, or via Java. So that's how a typical work in Hadoop ecosystem goes. Okay, so that was a quick way of looking at the Hadoop ecosystem. Now we will do a little deep dive in each of these components. Any questions at this point? Anusha, are you with me? All right. So regarding Uzi, let me explain again. So the way um, okay, so before I continue, Anusha, it'll be great if you could tell me a little bit about your background. Hi, Mehdi. Mehdi is also joined the class. I did not know since you have joined. Okay, okay. All right. Hi, Mehdi. Welcome to the session. I think you must have already gone through these sessions, isn't it? All right. So, yeah. All right. All right. So, we have Anusha and Mehdi in the class. And Mehdi, it'll be great if you could give a quick view. And I'll make you also a panelist so that you can see the chat. Hi, Mehdi. So, right, right. I think it's the time to introduce both of you. Both of you. All right. So, coming back to the topic which we were discussing, actually, so yeah, Mehdi, could you introduce yourself a bit, and then I'll mm, let Anusha introduce herself. You're
Okay,
unmuted.
sure. Hi, good morning. My name is Mehdi. I work for DoD in Washington, D.C. I'm working as a Spark developer, and I'm using Kafka, and I'm using Spark streaming. And now that's it. I'm doing this right now, and I'm very interested in um, machine learning and analytics tools. And last time I learned Spark and Kafka from Sandeep previous session. It was very helpful. That's why I joined again his analytics session. I, he is very detailed and very helpful. I never see any other session a handful experience and provide the handful all installation, everything. So I'm really appreciate. So
All
I
right.
stay with no big data team. Thank you very much.
Okay. Thank you, Mehdi. I'm really, really happy and glad that you liked the session. Anusha, do you want to introduce yourself? You want to unmute yourself and introduce? All right. All right. So, yes. Hi, Anusha. And Anusha is a kind of fresher into the industry. So, welcome, Anusha, to the big data sessions. And you are going to really like the sessions. And I'll try my best to explain the concepts to you. And, all right. So, great. All right. All right. Okay. All right. So, great. We are starting to. Okay. So, there was a question from Anusha. The question was, then what's the point of having Uzi? Okay, what's the point of having Uzi? So I was explaining that in a typical work in the big data analytics industry, you have many steps. You have many steps that you go through. You start with gathering data, then you clean the data, you format the data in the form that your analytics engines want. Let us say, for example, you are trying to make You are trying to generate the recommendation. What do we mean by recommendation? Recommendation means based on what people have voted for which product. Say a user said that they like this product. You must have seen on Amazon the recommendations. So to do the recommendations, to do the a great recommendation for users, there could be many kind of recommendation, whether for products, sometimes it's for the content, sometimes it's for the text. So to do that, you need to use these kind of tools like Mahat. We will show you how to do all of these things as we go forward. Okay, but but these tools like Mahat, they want the data to be formatted in certain way. For example, in typical case, Mahat wants the data to be in three column format. First column being the user ID. User ID should be a big number. Product ID, that is second column, and third column is the rating from 0 to 5, right? So, and when you have the raw data could be very, very strange. Raw data could be that you're given the full list of the website logs. What is a website log? When you have a website like we have no big data, and user, or you have a website like Amazon. I was with Amazon earlier. So we had this web logs where whenever a user is visiting our website, we make a record of which user visited which page at what time and from which IP and what was the session details. So we record all of these details in files which are called web logs. Now, web logs, while on one hand you have these web logs containing line by line saying this user, this URL from this IP at this time, this user, this IP from this time. So you have this humongous text on one hand. Now, on the other hand, Mahat is asking you that, hey, give me user ID, product ID, and the rating. How much? So, what do we mean by that? You will have to form the ratings based on this raw data. And how can you form the ratings? So, in case of Amazon, what we did was we first we cleaned up the web logs. Okay, we just picked up the records which contain the product details, as in you visited this product detail. First was that one. So from that we inferred that you have visited a particular product these many times. Okay, so Sandeep Giri visited um, laptop page three times. Sandeep Giri visited this product these many times. Then Sandeep Giri added this product into the cart. So we have all of these details. Now, once we have these details, from this we can form affinity. We can say that if this user adds a product to the cart, we give the user as 2 out of 5. Okay, if the user has clicked on buy now, then we give the user as 3 out of 5, which means this user really likes this product. So in the same way, we sum up all the values, we normalize it. Normalize means bring, stretch the data, push the data to bring it to something between 0 to 5, the way we bring marks into something like A B C D E F, right? Similarly, we do the normalization of the data saying that, okay, this user has visited this page these many times, this user has visited this page this many times, and then we normalize it. Now, to do all of these tasks, if you have millions of pages, summation of big numbers is also a big problem. Therefore, you will require tools like Piglatin and Hive to convert these big data logs into something which Mahat wants. I'll give you another example where I was working with InMobi, and again, my role was to build a good recommendation engine. Okay, so at InMobi again, what was I doing? Let me take a step back. So what does InMobi do? What does InMobi do? InMobi is basically a kind of an advertiser. Okay, so when you play games on your phone, you generally see these ads coming in between. Those ads are mostly coming from either AdMob from Google, or they are coming from InMobi. Okay, and most of the times the ad is not displayed. So those were the times what I did was, instead of displaying ads, I was displaying what kind of apps do you like. Okay, what the recommendation of various apps, and how was I able to do that? Every time an ad is displayed in your game, every time an ad is displayed in your game, we have a record that this guy or this person was playing this game and requested for the ad at this particular time. Now I have a record that Anusha was playing uh, uh, the temple run. Three times the request came to us on three different dates. Similarly, I have a record that Mandy has been using say file manager uh, five times. Now, based on these kind of data, we had similar data from various people, and this data is again from the web logs, because when you request an advertisement inside your game, it's basically that ad slot is nothing but a browser. The ad slot is nothing but a browser, and that browser is hitting our server, and our server is making a note of that who is asking for the ad, who is asking for the advertisement, right? So while you're playing the game, all of this thing is going in the background. The ad slot, which is a small browser, invisible browser, which is sending a request to us asking for the ad, and also telling us that this person is playing this game at this point of time. All right, so based on this based on this, we were trying to do app recommendation. We figured out that there are uh, so many people similar to Anusha's behavior, and they have been playing other games as well. So we started doing the cross recommendations. Okay, so these are the few interesting aspect about the recommendation. Now, on one hand, we had 200 terabyte of web logs, okay, out of which we had to clean these web logs and generate the recommendation. Now, 200 terabyte is a huge data. 200 terabyte is a huge data because it will take 5,000 into 200, these many seconds. 5,000 into 200 seconds, which is around uh, uh, 2 into 4, around 400 hours. Okay, to just read 200 terabytes is going to take 400 hours. Now, these kind of problems cannot be solved using one computer, and that's where we were utilizing this whole Hadoop ecosystem to solve our problems. Okay, so now when you do all of these things, first you have to push the data to HDFS, then you have to clean the data, form this kind of three column data for recommendation or Mahout, or you might have to feed it to some other pipeline. So all of these steps in a single project, there are many steps, and these steps have some certain order in which they have to be done, and they have certain orders in which they have to be executed, right? And that could only be done if you have a workflow engine which helps you in that, and that workflow engine is Uzi. Okay, so Anusha, was I able to explain? All right, no, all right, let's take a 5 minutes break. Hi, I'm back. So, are you guys back? Should we start now? All right. All right. So, okay. So, if you have specific questions, you can ask now. So, you were saying that other things are not clear. So, if you have specific questions, which part is not clear? So that will be a big help for me. Yes, Anusha. Do you have specific questions for me? So, okay. So, was Uzi clear now? All right. Great. Great. So, I think I misread your answer. Okay. Good. Good. So we were discussing about the various component in the Hadoop ecosystem, and I choose to do it quickly. Now, before we jump into understanding Hadoop distributed file system, let's first establish why do we need a new file system? What is the point of having a new file system? So, so let's try to understand what happens when data grows bigger. All right. Only then you will be able to appreciate, and that would serve as a motivation to learn the HDFS. All right. Let's say, let me ask you this: you are living in a hostel, and or you're living in a big hostel, and all of your classmates and the college mate decides to build 100 TB data store. Let's say you decide to store all your movies at a single place. Okay, so that everybody can store the movies at the single place and they can play from it. Now, your estimate is that you would require around 100 terabyte of space. How will you build such kind of storage? Anyone? How will you build such kind of storage? Okay, Anusha says that we will have 100 different systems. Okay, good. On a network, on a network, 100 different systems. Brilliant. Any other suggestions at this point? So if you have to store 100 terabyte data, how do you generally go about it? Without, if you don't know about what is a Hadoop and you don't opt for any cloud service provider. Good. So the general answer is that we go for 100 different systems. All right. So what we do is we call this kind of mechanism as building a network attached storage, that is NAS. This is NAS, network attached storage, or storage area network. And typically, what happens in storage area network and network attached to storage, or in our typical systems which we generally build, we will take 101 terabyte hard drives, make 100 subfolders to mount these. Okay, let me explain again. So you got 100 computers, you put one hard drives in each, and in case we want a backup of each one, we generally put 2 terabyte hard drives on each machines, one plus one, so that one is just the backup and other is the real storage. So you basically bought 200 1 terabyte hard disk, two drives on each computer, and connected all these computers together. And in some of these computers, we created something called one folder named main folder. And under that folder we created subfolders, and these subfolders were basically the network mapping to each drive. So this main folder is basically a folder created on computer 1, computer 2, computer 3 parallelly, and under this main folder we created 1 2 3 4 5 6 like that for each of these hardware and mapped it, so that when a user is writing to the first folder, it's going into first drive. Is user is writing to the second folder, it's going into the second drive. Second drive here is the second computer, and there is a backup on each computer. All right, sounds good to you? This is what you meant, Anusha? Mehndi, you have gone through this exercise, I guess. All right, so great. uh, all right, so now we have uh, okay, so I think I'll make Mehdi as also as organizer, so that he can see the chat. Okay, we have just made him panelist. I think he can see the chat, I believe. All right. So now coming back to this question, where you have these hard drives. So do you see any problems with this kind of structure? Do you see any problem with this kind of structure? Very expensive. Okay, that's good. Anything else? Traffic issue. Okay, good. What happens when one computer goes down? Anusha, have you started the recording? Please start the recording. Okay. I'm recording just as a backup. I want one more copy. There is a record button on this go to webinar. Just click on that. All right. So again, we so the way I'm trying to keep the backup of my recording, do you think that backup would be a problem in this circumstance? Yes, that's correct, Mandy. We required distributed storage system. All right, good, very good answers. So the general problems would happen with this kind of architecture. What happens when one of the machine's network is giving a trouble? Because machine failure or machine's network failure is a very common situation. Operating system failure on a machine. Okay, so those are the very many kind of reasons why a machine could fail. All right, heating issue might be there for some machines, and there are many reasons why a single machine fails. Okay, so in the network we just formed, in case any of these nodes go down, there is no failover, there is no backup, there is no failover. Backup and failover, the difference is, if in case of backup it doesn't come live quickly, in case of failover it comes live quickly. So that is the first issue. Second issue is, how would you distribute data uniformly. You got 100 folders, and if you have used a computer and you try to use have multiple hard disks, and you try to store movies and music on those hard disks, you would always have this challenge of that my C colon is full but my D colon is empty. Now since my C colon is dedicated for this, my D colon is okay. All right. All right. So Anusha, just try to see if you have a record button somewhere. I'm not sure. I do not use Windows. So, all right. So I will make. Hey, Mehdi, I'm making you the organizer as well. Okay. So that you can also. So, if possible, can you, Mehdi, can you start recording? I don't want to take that risk of losing the recording. Okay, so if you are on Mac, do you see something, a tab called screen sharing? Under that screen sharing, at the topmost tab, you will see a record button. You clicked on that record button? Awesome. Great, great. Anyway, now I have added Mehdi also in the organizer. So we are three organizers and for this session. Okay, so all of you have a control of the session. All right, great. So we were discussing about how do you distribute data uniformly? So generally the problem happens when you have multiple hard drives because there are boundaries between the hard drives. So you can't, so some of the drives will be empty, some of the drives will be full, and then you always are in a shuffling mode. You're always trying to figure out how can I fit the data properly on these hard drives. So since you have these many folders, you will always face this kind of challenge that what to keep where. So generally, in these kind of circumstances, what you do is you make a list of files on a paper. If you have to do it manually, you make a list of files, you make a list of sizes, and you make a note of which folder is it in. Okay, is it in drive 1, drive 2, drive 3, drive 4? Where is this? So so that's how you could try to do the distribution, but you will always fail to fit it in, and that becomes like never ending challenge for any sysadmin or anybody who's trying to manage this kind of thing. Now, is this the best value for money? We are buying 1 terabyte hard disk. We might have the hundreds of similar smaller hard disks lying around, but we cannot use those because if there is a smaller hard disk, we may not be able to fit in the bigger file. Okay, now the next point is, what about increasing accessibility? What do we mean by increasing accessibility? Okay. All right. What about increasing accessibility? What does it mean? Imagine this. Today is Independence Day and everybody wants to watch the same movie. Now, if it is so, in this kind of architecture which we have just discussed, it will be the same hard disk, and effectively if there are more than one person accessing the hard disk is a physical device in which there is a header which moves, and this header will jump back and forth trying to cater to multiple users, and at the end of it it will give up. At least it will hurt everybody's using movie experience. Everybody's movie experience is going to be really really bad. Therefore, accessibility is a very important task. Now, what about scaling out? What does it mean by scaling out? Today, our requirement is 100 terabyte. Tomorrow, we might need 120 terabyte or 150 terabyte or maybe 200 terabyte. You never know. Therefore, what happens when we need bigger space? If we add more computers, we'll be able to auto balance it, or will we have to do a lot of juggling to balance it? So those are the challenges with this file system, and that's where the HDFS comes into play. Okay, I hope I have answered your questions with respect to this. Okay, so now I believe that all of you would be convinced that we require HDFS. All right, so the primary and most important part of HDFS is the name node. Okay, so HDFS is made up of two kind of computers. There is a single or master or the king. There is a single node called name node. We sometimes call it admin node as well. Okay, we sometimes call this as admin node. Now this admin node is like an index. It keeps track of which file is where. While there are many data nodes, in case of 100 computers, we will have 100 data nodes and one extra computer dedicated to name node. So these data nodes will contain the actual movies, while name node will just keep a list of records noting down which movie is where. That is name node or admin node. All right, so that was about name node or admin node. Now this admin node is basically a metadata, and when we say so if you have a cluster, when you have multiple computers, one of them we designate as name node and rest of them are data nodes. Now this name node or data node, when we say designated, it means it's like a program running in the background listening on a port. Okay, every program, every service which is responding to people's request is running in the background and is listening on a port. Whenever there is a traffic that comes to that port, it responds. For example, a web server who is responding to your request. When you say nobigdata.com in your browser, it hits our server, and that server is having a web server running on it. It's a process which is running in the background, listening on a particular port and responding to people's questions. Okay. Similarly, name node is a process listening on a particular port, and same is the case with data node. Now, when you have name node and data node in an ecosystem, so we will be able to store the data. Actual data is stored in data node, while list of files and which file is where is stored in name node. And name node keeps the whole data into the disk, having a copy of it in the disk. Okay, so name node keeps all of the memory in all of the data in the memory. Why? Because it has to serve the users really fast. If somebody comes and asks name node, where is this file? It quickly tells that, hey, this go to this particular machine and ask for the file. So name node has to be really, really fast. Therefore, name node keeps the data in the memory. All right. Now there is one more detail to it. While we just said that the actual file content is stored in data node, all right, and each file is broken down into blocks. Each file is cut into small, small parts and distributed across the cluster. Okay, so each file is, earlier it used to be 64 MB, but as of today, this chunk, this block is moved to 128 MB. Why 128 MB? So that the blocks are bigger. Okay, so now why do we need blocks? Why did we cut the files into blocks? Okay, I'll come back to the question like who cuts these blocks and how does it happen. So what's the point of cutting the file into blocks? Instead of storing the whole movie in one node, Here we are cutting the movie into parts, maybe 8 parts. Okay, 128 MB and is equal to 8 parts in one gigabyte. So if a movie is of 1 gigabyte, there will be 8 parts to it. Last part is generally smaller because not all movies can be of exact 1 gigabyte size. So or not all file could be exactly in a multiple of 128 MB. So generally the last part is smaller than 128 MB. Now, so the reason why we split it into blocks is it helps us fitting bigger files into smaller disks. It leaves less unused space on the disk. It optimizes the file transfer. It distributes the load onto multiple machines. All right. So if you are breaking down a file into smaller blocks, what will happen is at most the space which is unused on this will be lesser than 128 MB. Similarly, in this case, so there will be less unused space left on each disk. Next is, what if you have a hard disk of say 4 gigabyte, or let's say you have a hard disk of 80 GB, but you are trying to store a movie of 81 GB. There are some Blu-ray which are actually of 81 gigabyte. Now you cannot fit those kind of movies onto this disk. But if you break that into parts, it is easier to store it. Now, the other benefit of having blocks is it optimizes the transfer in the sense that if we have to rebalance the nodes, it becomes easier. Okay. So instead of moving the whole file, you can just move the block from one node to another and they will both have equal amount of storage consumed. Okay. So that helps us in rebalancing and optimizing the transfer for rebalancing. Now, it also distribute load onto multiple machine. Going back to our example of Independence Day when everybody is watching the same movie. So if you are watching a single movie, so one movie is divided onto 8 computers because it has got 8 blocks. Now, so 8 users can actually watch the movie if these 8 users are offset by few minutes. Okay, some people just started watching the movie, some people had been watching for like before 15 minutes, and some people will start after 30 minutes, so they can actually multiple users can watch the same movie at the same time. Okay, so that's a benefit of breaking down into the blocks. So this was a very big interesting aspect of having the SDFS blocks. The second is each of the data blocks has got a replication factor of 3. The data is copied to 3 nodes parallelly. Okay, so by default, the replication factor is 3, which means every block has got 2 more copies. And what's the point of having multiple copies of the block? So that in case one node goes down, we have the backup. Okay, so some of you might say that what's the point of having replication factor as 3? Why not 2? 2 must have been sufficient. So here the risk is little bigger. Why? Let's imagine that your file is of 1 gigabyte, which means it has got 8 blocks. Now these 8 blocks, imagine that all of the 8 blocks are on 8 different data nodes, which means that in case any of the data node goes down, your file goes down. You will not be able to recover your file because in case any of the data node goes down, your file will go waste. So to im- in to make the probability lower, okay, it is generally better to keep three. Okay, 3 copies of each block. Now out of these 8 nodes, in case let's say we are keeping 2 backups. Now there are 16 nodes. Out of the 16 nodes, in case there are 2 nodes that have gone down, and those 2 nodes are the same nodes on which the copy is there. So, so there are still the chances. But if it's on 3 nodes, which means 24 nodes, out of 24 nodes, exactly those nodes going down which have the first copy is very, very low. Therefore, it's better to have three replication as compared to two, because chances of two nodes going down is far higher. Okay, all right. So that's why if you are having a very good disk which do not fail, for example, you are having solid state hard drives. In case of solid state hard drives, you can have a replication factor of 2. Okay, solid state hard drives are fast. Second, they are generally costlier and provide less space and are costlier, but they are very reliable. Okay, so there's a meaning of a replication factor. Now, when you replicate when you replicate data, no two copies can be on the same node, not even same disk. We are talking about same node. If there are two disks on one node, still one block will not be duplicated on those two disks. It will be on a different node. So no two copies of a block goes onto the same machine, same data node. Why? Because if we put the copy on the same node, it's of no use, because if the node goes down, the data is not accessible. All right. In case in case a particular data node fails, the lost blocks are copied to other nodes. Now, what does it mean by blocks? Let's say data node 1 went down. When a data node goes down, there will be some copies of all the blocks that have been lost. Now, the total number of copies left will be 2, right, for each block, because one block had just lost in this particular system. Now, out of these two, now the replication factor of these files which have lost because of this particular data node has reduced. Now, to bring it again to 3, it starts replicating the blocks from 2 to 3. Okay, so when a block gets lost, there is still two copies left in the network. So immediately data nodes start copying that block, and to make it again a replication factor of 3 copies of the same block. So that's the reason why we have the replications. All right, so the way we imagine generally is, all right, so one more thing. Who slices the data into blocks? It is the client library, the command that you use to store the data into a cluster. Okay, is that command which slices the data into blocks. Now this command, so generally the way we imagine that our user will come to name node, and then it will ask name node to store the file. Name node will go to data node and store the file, while end user will never get to know about data node. That is not the case. The flow of the communication is like this. The client, the user uses a command called client or a driver, like we have JDBC driver for our SQL execution. Similarly, we have here a command that goes to the name node that our user wants to read or write this particular file. Name node replies back and says, hey, don't bother me. Here is the name of the file. Go directly and talk to data node. Don't talk to me. Okay, if you want to read the file, go to that data node and read the files, read the blocks. Here is the list of blocks, here's the list of data nodes which contain your file, and these are the blocks. So all the details about the blocks of your file is given by name node back to the client driver, and client driver internally does all of that magic. So it is the client driver who slices the file into blocks. It is the client driver who talks to name node, gets the blocks, and then again goes to the data node and get those blocks which have been given by name node. Name node just gives the list of things. It doesn't really give the transfer, because if name node started doing everything, then name node will be the bottleneck, and name node will, so the whole objective of a great file system will be lost. All right. Do you have any questions at this point for me? All right. So that was the architecture. So a little bit more. The client comes to write the data. Okay. Client comes to write the data to the name node. So if you want to write the data to, you first go to the name node and tell the name node, hey, I want to write the data. Now name node will get back to you saying, these data nodes are free, why don't you go to these data nodes and write the data directly on those data nodes, and those data nodes internally will do the replication. And then once you are finished with writing to the data node, you go back to the name node and tell name node that, hey, I'm confirming that I have written to the data node, please update your metadata, please update the index. Now the name node will actually confirm that you have written the file. Okay, so that's about the client's behavior. Clients talk to the name node and writes the data into the metadata and gets the job done. Okay, so similar is the read operation. User comes to name node and tells, hey, I want to read this file. Name node tells you that your file is broken into these many parts and these parts are located on these machines. You can go and directly get the data from any of these machines. Now the client will pick up any of the machines which are closer to it and will start reading it. So that's the magic being done under the HDFS. I hope everything is clear. Do you have any question to me, Anusha? Great, great. Feel free to ask the questions because my sessions are generally oriented towards asking more and more questions. Okay? Because nothing can be taught without asking questions. Nothing can be learned without asking questions. Okay, so feel free to interrupt and ask the questions at every point of time. All right, so right, otherwise yeah, if you have any doubt at any point of time, feel free to ask, even if you feel that it's awkward and I might sound very dumb, still you ask the question. Because none of the questions so far I've seen in any of my classes, none of the question is dumb question. Okay, great, great. All right, now, all right, that was the file system. That was the file system. Now we want to go ahead with the operating system. Operating system as in not in terms of device managers, but in terms of execution of your program. The peop the guy the system which takes care of execution of your logic across the cluster. Okay, so we will go into the compute engine and understand what goes on inside a compute engine. All right, so for now, let's talk about, so there are two kinds of organizations. One is a freelancer, other is a company, right? So, or a team. So if you want to get done your work via freelancer, you just directly talk to them and get it done via them, and they will work on it and get back to you. Now, what if you have a bigger work, you have a bigger project, and you want to get it done by a team? Okay, so you generally have this person called team manager or project manager, project leader, or whatever, engineering manager, this and that. There are many names for the same guy. Now there will be always this leader, team leader, or whatever, who will interact with you You will tell him that, hey, I want to get this thing done. I want to get my website completely done. It's up to you how you get it done. Okay. Now, if this guy is doing it by himself, then it'll take a long time. He will have to make the logo, he'll have to design, he will have to do the screenshots, he will have to do the backend, he will have to do the database programming, and he has to do a lot of things to get your work done. Now, what if he has a big team? What he will do is he will assign one work to each person, and when those people finish the work, he will update you. In case one person goes on leave, he gives the work to somebody else, same work, and and that's how it goes on. And that's exactly the way the compute engine or yarn works. In the most simplistic way, if you look at it, there are two kinds of nodes. One is called job tracker and other is called task tracker. You, as a third party or external person, you tell job tracker that, hey, here is my work. Can you get it done? Okay. Here is my work. Here is the description of my work. Can you get it done from your team? Now, this job tracker will go to all the task trackers and assign them one part of the whole work. Now, each task trackers will be working on it, solving your problem, and then get back to you. Get back to the job tracker. Get back to the job tracker. Job tracker will mark, okay, fine, this guy is doing good, this guy is doing good, this guy has finished the work, but third guy is not responding. So job tracker continuously keeps on pinging all the task trackers. In case any of the task tracker goes unresponsive, it assumes that that person has maybe had gone on a leave or something else. So it assigns the same work to somebody, and all the work done by the previous task tracker is is deleted, is ignored. Okay. So this is how a bigger work is done by the way of so many processes. Okay. Now, here a big question is, then what kind of work are we talking about? We are talking about a data intensive work. Let us talk about a very simplistic case. Let's say, let's say you have 200 terabyte of data. Imagine that. You had 200 terabyte of data. That data is stored on data nodes. Luckily, luckily, most of these task trackers actually run on the data nodes. Okay. So on you have 100 computers. Let's stick to our 100 computers example. You have 100 computers, and on these 100 computers you have one process running called data nodes and other process running called task tracker, and you have 101th node on which you have put a name node, and also you have put a job tracker. Now you ask this job tracker that, hey, here is my 200 terabyte data. Can you find a particular line that contains my name? That contains my name called Mehdi. Can you give me all the lines in this big text file or text files of 200 terabyte? Okay, just can you just find all the lines in this 200 terabytes and let me know what are those lines? Okay, now there is 200 terabyte data. As I told you, if there was one machine who has to go through all of this, it will be like too much of task. Therefore, therefore, job tracker tells the task tracker. First, job tracker finds out that which all node contains the data that you're talking about, because we have, as we have just said, that you have got 200 terabyte data, and that too is stored on HDFS. And if this 200 terabyte is stored on HDFS, that means it's going to be on blocks, and when it's in the blocks, that means it's distributed and over all these 100 computers. So you have 100 computers, 200 terabyte data, and all 101 computers. One computer is dedicated to name node and job tracker, and on 100 computers you have data nodes and task trackers. So The data is distributed across the cluster on the data nodes. All right. Now you go to job tracker, that here is the name of my file. Can you just find all the lines that contain my name? Now this job tracker is clever person. He'll go and ask name node that, do you know which all machines contain the block of this file? Then name node will respond, oh, these files, fine. These are the blocks that contain the blocks. These are the data nodes that contain the blocks of this file. Now job tracker will figure out who are the nodes which are near to the data. Why? Because transferring the data is something really, really horribly slow. So if the logic is executed on the same machine, then it'll be really faster. So job tracker will call up all the task trackers who are on the same machine where the data block is. Okay, he'll call up all the guys, say finding out who are the task trackers close to the data and ask them to find out. It'll ask all of those task trackers to find out your name in the file located on each of the disk. Now you see the beauty of it. There are a couple of things we did here. First, we divided the work. Instead of one person going through all the files, we made so many nodes go go through the files parallelly. Okay, and one more clever thing happened, that the data is already on the task trackers, so there was no transfer involved. So suddenly the task which was going to take around 2 years finished in 2 hours. So these are the clever optimizations, these are the clever system which makes impossible task possible, which makes some mammoth looking work which is 200 terabyte possible. Imagine that none of the supercomputer could match the performance of these computers. Okay, so if you have bought 1,000 computers with 100 computers, 100 computers each costing $1,000, it will be 100,000, and in 100,000 you can hardly get a big supercomputer. Okay, and this system will be far, far, far more efficient than any of the supercomputer available as of today. Okay, so the cleverness is being able to divide and distribute the data, being able to distribute the computing on so many nodes. Now the same diagram shown in the two forms. One is job tracker. Job tracker is talking to the task tracker is getting the tasks done, all the clients are talking to the job tracker, and this way. So I hope this is clear to all of you. Anusha and Mehdi, I hope I was able to explain. Great, great. All right, brilliant. So, all right. So this is where the now a big question occurs, that we were fine here. We just have to find the text. We just have to find lines containing my name. But what happens when my processing is really complex? What if what if my problem statement was like this? Sum up all the uh, line numbers. Sum up my age. Okay, let's say there is this 100 terabyte of file containing each line containing name of the person and their salary, name of the person and the salary. Now your objective is to find out the all the names that start with M and compute their average salary. So you want to find out what is the average salary of the people whose name start with M. Now, finding out the name of the people who are starting with M is easier. You can divide the work parallelly. But finding out their average value, you need to aggregate you need to summarize. That's where the second phase of work comes in, called reduce. In reduce phase, you after you have finished the work on individual node, you gather the data and you try to do the computation of aggregation. Okay, so we will continue the discussion on MapReduce tomorrow, and till then, I'll be giving you an assignment. I'll be giving you a quick assignment of interacting with the file system. So, were you able to see your login password in the system? If you go to no big data, so Mehndi, as opposed to our class previously, now we have individuals account on the Cloud Labs. Okay, so here you will find your login password. Right now for me, my account has expired, so Cloud Lab is giving error for me, but for you it would be working fine. Okay, here you will see the login password. Use those login password to log in into the what do you call, CloudX Lab. Okay, not here. So you go to Hue. I'll use some other teams login for now. Okay, because I have access to multiple teams. But you use your own big data analytics class. Anusha, are you able to see the login password for yourself? So we'll go into MapReduce detail tomorrow, but let's just go through the HDFS once. Okay, all right. So you can go. I'm just trying to find out a login password for myself. Uh, I don't have one. Yeah, I'm just taking from any other team. Previously, we used to have one account for the whole team, but now from this session onwards, we have decided to go with uh, one per person account. Okay. So I'll just explain to you what are the things before we jump into the. All right. So we have something called Ambari. Ambari is for sysadmins. Okay. Ambari is for sysadmins. Sysadmins use Ambari to keep an eye on the network. Okay. Sysadmins use Ambari to keep an eye on the network. So I'm logging into Ambari. Using Ambari, people install the software. You remember we talked about Ambari here? Okay. Ambari is your provisioning manager, which helps you manage the network. So you can see that we are able to see the cluster usage. Okay. You can see that. All right. Similarly, you can see the cluster load from time to time. All right. You can see that this part is idle, this color, and rest of it is user average, and so on. So this is Ambari. Ambari is good if you want to install more nodes, if you want to add more nodes to the system. Now here is Hue, and also at Ambari you can see what are the how many machines are there. Also, I'll show you a few more things. Here, if you go to the dashboard, it has got HDFS at the top. HDFS shows you that there is something called name node, and there is something called secondary name node. Secondary name node is like a backup of name node. In case name node goes down, you can recover from the secondary name node. Okay, so we have secondary name node, and there are data nodes. You can see name node and data nodes. Whatever we learned just now, there are three data nodes and one name node. Okay, Now, if you go into name node, it will show that it is installed on this particular computer. These are private IPs of those computers. And if you go into the data nodes, data node is installed on all these three nodes. It shows their how many cores are there, their disk usage, their load average, right? So this is the real instance of the cluster. Now, if you go here, you can see that there is this full UI. This for people who are trying to interact with the tools, meaning you are trying to create a folder, upload a file, run a program, run a script, run a SQL query. If you want to do all of that, then you come to Hue, which is running on 888 port. Now you can go to the file browser. So this is our HDFS. As opposed to what you have seen earlier, here you can see that this is a nice folder structure. You can create your own folder inside it, upload file to it, and then test if it's working or not. Okay. All right, I cannot upload that. All right, let me try to upload something else. Let me try to upload. I cannot upload this. Maybe I can upload this. All right, let's say I'm uploading this MacBooks. So you can see that this is getting uploaded. All right, it'll take some time because it's a little slow. My up speed is a little slow. All right, so this is HDFS. You can interact with HDFS either from here, or you could go to the terminal. You could go to the terminal here. This is the terminal, and using terminal, this password and login. If you are not comfortable with terminal, you don't need to go through that route. Okay, if you're comfortable, then you can use that. All right, so you can interact with the Hadoop file system from the console. If you can use Hadoop FS, and then you can use other commands. All right, uh, okay, is it breaking right now also? Looks like my network is bad. All right, we will we will continue from here tomorrow. All right. All right. So we will continue the discussion tomorrow. Have a great day. Try to interact with Hugh and try to interact with the terminal. Okay. So we will have the discussion further tomorrow. You will see a quiz in your session. You will have to answer to that quiz, and see you tomorrow. Bye bye. Have a great day. All right.